Hey everyone, welcome back. Today, we're actually putting on our detective hats for this explainer, because we've got a massive, everyday mystery to investigate. We're diving deep into the world of physics to track down something that literally vanishes right under our noses every single day. That's right, we are officially becoming energy detectives.
So here's the central mystery we've got to solve today. Think about it. When you're running around outside, or when your phone battery slowly drains over the afternoon, or a loud car speeds down your street, when you use all that energy, where does the quote-unquote lost energy actually go? Does it just magically poof into thin air? Well, spoiler alert, no way it doesn't. But tracking it down, that's going to require some serious sleuthing.
Here's our trusty detective's manual for today. First, the missing energy mystery. Then, Step 1, track the change. Step 2, spot the waste. Step 3, watch it spread. And finally, the point of no return. Let's get right into it.
Part 1. The Missing Energy Mystery.
And that brings us to step 1 of our manual, track the change. All right, so our investigation kicks off with a fundamental rule of the universe. Every single time you make something happen, whether you're burning wood for cooking, walking up a flight of stairs, or just riding a bike, energy is transferred. It simply changes forms. Energy never just gets consumed and vanishes. Let's look at a real-world suspect, like a motorcycle. The gas going into that tank, that's a highly concentrated store of chemical energy. The whole point of the motorcycle's engine is to take that chemical energy and change it into useful kinetic energy. The energy of movement, so the rider can actually speed down the road.
But here is the shocking truth about that energy change. You'd hope all that super expensive fuel turns straight into forward movement, right? Actually, no. Only about 1/4, just 25% of the chemical energy in the fuel is used for actual movement. The other 3/4, a massive 75%, totally wasted. So what forms does that waste take? Well, it changes into thermal energy, which makes that huge metal engine blazing hot, and sound energy, which makes it incredibly loud as it roars by.
Let's check out another everyday suspect, light bulbs. Lamp A and lamp B have the exact same super simple job, which is to change electrical energy into useful light energy. And to the naked eye, if you put them side by side in a dark room, they look like they emit the exact same brightness. But beneath the surface, the way they transfer energy is completely different, and they waste wildly different amounts of energy to get that exact same result. It's all about how they handle that incoming electrical energy. Get this, lamp A only changes about 15% of its electricity into actual light. That means 85% is wasted as thermal energy, or heat. Lamp B is way better at its job. It changes 50% into light and wastes 50% as heat. So even though they light up the room equally well, lamp A is basically acting way more like a heater than a light bulb.
Moving right along to step 2, spot the waste.
Now, to figure out where all this wasted heat actually goes, we need to nail down our core vocabulary word for this investigation: dissipated. Dissipated energy is just wasted energy that spreads out into the surroundings where there is absolutely no use for it. It escapes, it leaks away, and it's completely out of our control. Picture this. You're heating water over a campfire in the woods. The goal is simple: change the chemical energy from the burning wood into thermal energy to heat the water in the pot so you can eat dinner. That's our useful energy transfer. But is all the heat from that roaring fire going straight into the water? Definitely not.
If we break down the campfire's energy transfer, we see dissipation in action. Sure, some heat goes straight to the water, but that thermal energy is also actively heating the rocks underneath the fire. It's heating the metal pot itself. It's heating the air all around the campsite and changing some energy into light to illuminate the trees. Plus, some of the heat is escaping straight up in the steam. Most of the fire's energy is just spreading out into the woods, completely wasted and totally useless for cooking your meal.
All right, step 3, watch it spread. Time to really put your detective skills to the test here. When you move away from a hot object, like that campfire, you feel less heat from it, right? The temperature goes down as the distance goes up. Think about how a graph of this would look. The temperature doesn't just stay perfectly flat, it drops off on a steady curve as the thermal energy dissipates and spreads out into the surrounding air. The further away you go, the weaker that energy feels, just because it's been stretched across a much wider area.
Another absolutely brilliant way to visualize energy spreading out is by using a ripple tank. Imagine a shallow, waterproof tray filled with just a little bit of water. This super simple setup actually lets us easily track energy as it moves, so we can watch exactly how it behaves over time and distance.
When you lift and then suddenly drop the edge of that tray, you are transferring kinetic energy directly into the water. That energy travels as a totally distinct wave, sloshing vigorously back and forth across the tray. But it doesn't just bounce back and forth forever, does it? Eventually it slows down and the water goes completely flat again. As the wave travels, the energy stored inside it dissipates. It spreads out and is lost to the edges of the tray and the air around it until the wave just disappears entirely.
You know, you can actually track this right in your own kitchen. Think like a scientist with a fresh, steaming cup of hot tea. If you measure the temperature of the hot tea every single minute and plot it on a graph, you're literally tracking the dissipation of energy. The higher the temperature of the tea, the more thermal energy there is stored inside it. But over time, that thermal energy dissipates. It spreads out into the ceramic mug, into the metal spoon, into the air in the room, until the tea is the exact same temperature as the room itself.
And that brings us to step 5, the point of no return.
We've tracked the energy, spotted the waste, and watched it spread. But what does this all mean for us? Well, here is the harsh rule of physics that every energy detective eventually has to accept. Dissipated energy cannot be recovered. You can't just gather up all the thermal and sound energy that leaked out of that loud motorcycle and cram it back into one place to use again. Once it spreads out into the environment, it is gone for good. It's a total one-way street.
And crazy enough, this isn't even a new discovery. Let's travel back to the year 1845. A scientist named James Prescott Joule was totally obsessed with where energy came from and where it went. He built this brilliant machine. He let a heavy mass fall, pulling on a string. That string turned a piece of wood, which spun a paddle inside a sealed container of water. Joule discovered that the kinetic energy of the falling mass and the spinning paddle actually increased the temperature of the water. He essentially proved that mechanical energy transferred directly into thermal energy. At first, people literally didn't believe him. His ideas challenged everything people thought they knew about how the world worked.
But Joule was totally right, and we see his principles everywhere today. Just look at a thermal image of a modern car exhaust. Those bright, glowing colors represent intense heat. Just like Joule showed that movement creates heat, modern engines that take chemical energy to make cars move will inevitably create massive amounts of wasted thermal energy. And just like we learned, all that glowing heat pouring out of the exhaust pipe, it just dissipates into the cool air, completely and forever unrecoverable.
So, my fellow detectives, we've solved the mystery. The missing energy isn't completely destroyed. It's simply dissipated, spreading out as useless heat and sound. But I want to leave you with one final massive question to chew on. If every single time energy is transferred, a little bit of it dissipates, and we can never ever get that dissipated energy back, what happens millions or billions of years from now when the entire universe runs out of concentrated, useful energy? Think about that. Thanks for joining me on this explainer, and keep your detective eyes open for energy dissipation in your own lives.